Well, thank you very much. I'm Stan Mack. I'm the Global Business Manager for the Clean Air business within BASF Corporation. I also happen to be the President of ICAC, the new President, so I do appreciate this opportunity and to speak with all of you. It's a very good association. We're 80+ companies that make all this equipment. You heard a lot of things today about how a lot of innovations have gone on. The mercury was just one example of how things, years ago, the EPA was looking to try to get $35,000 per pound of mercury. It's probably down to $1,000 or $2,000 per pound of mercury now. All that innovation comes from our companies. And so Karl and I are going to be, Karl will introduce himself. We're going to talk about VOC control. We're going to be back up and down ourselves. We're going to focus in on the back end of this, talks a lot more about methane control, the President's methane strategy, and some other things you can do that are not power plant related to control methane emissions. We're going to start out with VOC controls, looking at things thermally and catalytically. The most important thing is, what is a VOC? And although this seems rather simple, you would be surprised how many times this gets misused in the marketplace. And I'll give you one example. Right now, combined cycle power plants are the thing. People are out there. We provide CO and VOC oxidation catalysts to go into those power plants. And people consider VOCs almost like it's an element on the periodic table. It's like a very well-defined thing, but it is not. There are all different kinds of VOCs and all kinds of chemical structures. So when we're asked with a permit says we need 90% destruction of VOC, you have to, like we talked about before with mercury and speciation, we have to know what that is. Unfortunately, no one tells you what the VOC is. And the turbine guys can't tell you because the fuel changes every day. And they don't know exactly what VOCs are coming out of the turbines all the time. So it has a big impact on a lot of different types of markets. So for us, it's very, very critical to define what a VOC is. And when you come outside the United States, where they don't have the sophistication, it becomes even a much, much bigger problem. So the first problem we have is defining what is the VOCs and what are they trying to control. The sources, there's a lot of different ways you can approach this. There is, if it's a lot of compounds, you don't really want to try to recover it. And then you get into thermal and catalytic oxidizers or some kind of adsorbers, carbon absorption systems. If you have fewer than 3 VOC compounds, then you can kind of consider recycling or reusing the VOCs in some ways, and then you're using adsorbers. But if it's not feasible, you still have to go to thermal and catalytic oxidizers. But if it is feasible, then you can go into adsorptions. Kind of a general overview of the type of technologies and when you would deploy them. If you have a low concentration of VOCs, where the lower exposure limit is 0 to 10%, you can look at what's called regenerative thermal and catalytic oxidation. I think Karl will talk a little bit more about what we mean by regenerative. And the thermal efficiencies there are very high. It says 80 to 95%, but it's rare that you see anything less than 90%, I think, on thermal efficiencies. You could also use adsorptions in that area as well, because the concentration is low enough that you're not going to overwhelm the sorbents. You can use what's called recuperative. That's when you have higher concentrations of VOCs, and now you're basically going to burn them and recover some of the thermal efficiency, and that can be down to as low as 50% recovery of the heat that's generated from the burning of it. And if you have an LEL over 40%, usually you're dealing with an afterburner type of situation. And I think at this point, I'm going to turn over to Karl. There's one thing that came up this morning that I want to kind of point out. A lot of people are talking about natural gas like it's a well-defined element these days. Natural gas, as we see it today and what we see in the air pollution control equipment, is not what it was 10 years ago. And we're starting to see that it can impact air pollution control equipment. And natural gas combined cycle units, we're finding catalysts that would last for 10 years may not last for 10 days. The introduction of shale gas and not properly operated wells, shale gas wells, can introduce things in the gas pipeline. There are biogases now that can be introduced there. There's regulations in California that allows you to put some of that in there. It can have a significant impact on the operation of the equipment. So even though they say it's natural gas, we're finding it have a significant impact on the ability to operate these boilers because there are things in there because of it's not very well controlled what's getting into those pipelines. So I thought I'd just add that in here, and I'll let Karl talk over a little bit about some of this technology.
Thank you, Stan. My name is Karl Walby. I'm a senior key account engineer for Durr Systems. I've been with the company about 15 years. Just to expand a little bit on what Stan said, we're seeing an uptick in service business as a result of some of the different gases we're seeing because of the different compounds that are coming through the burners, and they are eating up some of the different components in our systems as of late. So depending on where our oxidizers are located, when sudden unexpected things happen, that's an important place for us to look, particularly if it's near one of the plays. In terms of oxidizers, I'm going to move through this sort of quickly. I'm sure a lot of you are familiar with oxidizers. It's a lot of the technology that's going to be posted in Larry's document, but when we deal with really high concentrations of VOCs, sometimes gases and liquids combined, we can deal with oxygen depleted environments or oxygenated environments. We deploy afterburners, and that's generally at the simplest level. It's a combustion chamber and a burner. It may be insulated with a thermoceramic fiber insulation, or depending on the constituents we're seeing, there's acidic compounds and so forth that can be generated. We may have a refractory line chamber. The design volume is very widely in these applications. The important features of these applications is that we can achieve super high destruction efficiencies when they're designed properly. We can get up to 4 nines and better in many cases. They're very energy efficient from the standpoint of we typically have very high heat loads in these systems, and we can then deploy other devices behind them to recover that energy, generate power, so on and so forth. A lot of times we deal with explosive gases in these applications. So in terms of the different trains that we have to assemble ahead of the system, the different burner arrangements, there's a lot of important explosive classifications that we have to meet. There's a lot of safeguards as far as deflagration arresters and flame arresters and things of that nature. And so normally we see these types of devices deployed in applications in industries where you would expect to see very high chemical concentrations, petrochemical, the chemical industry, pharmaceutical in many cases, and so forth. So that's just loosely what an afterburner looks like. You might be thinking about an enclosed flare. It's a little different than an enclosed flare in that we can handle both oxygenated and oxygen depleted gas streams with this device. This is just an example of the different fields of application of this particular device. On the front end of this schematic, you see the afterburner, and then after that, there could be many other different devices depending on the constituents we see and the things that we're generating as a result of the combustion process. So we could have SNCR after it. We could have a boiler to recover heat. There could be remaining heat after the boiler that we quench. We may need to scrub out acids later on. There's a lot of different things that could be cycled on and integrated into an afterburner system to take either advantage of the heat that the exothermic heat we're getting off of the combustion process, or to treat the other compounds that we're creating in the combustion process. And there's just a list of a lot of the different things that we see and that we deal with there. This is just an example, if you're at a site anywhere, that an afterburner can take on a lot of different forms and a lot of different arrangements. They could be horizontal, they could be vertical, they could have any number of devices connected up to them after the actual afterburner. Recuperative thermal oxidizers is somewhat similar to an afterburner in that you have an integrated heat exchanger that works with the actual afterburner. And basically, these are deployed on slightly lower concentration gas streams that do not have any liquids in this case. They're typically a combustion chamber, a burner, and they're integrated with a primary shell and tube heat exchanger. And that heat exchanger may be a tube type heat exchanger, or it could also be a plate and frame type heat exchanger. Generally, because of the size and the limits of the metallurgy, Those oxidizers are limited up to about 30,000 CFM for the most part. There's a lot of different heat exchanger designs we can deploy depending on the concentration of VOC we're receiving, and those may range anywhere from typically 45 up to about 70% thermal energy recovery. The pressure drop through this type of system is very low. The destruction efficiency is very high. Again, we can get up to 4 nines with this device as well. They're relatively simple to operate and maintain. We have to be careful with the amount of heat we recycle through the heat exchanger, or in terms of preheating the incoming gases, we could overload the limits of the metallic type heat exchanger. We have burners that we can deploy depending on what we're trying to achieve on the back end of the device. That may have dilution air, they may not have dilution air. We may be trying to achieve very, very low NOx levels with these devices as well. So it really depends on the state we're working in and what the regulatory requirements are as to how we would tailor this type of a system. In the past, probably from the late 80s through the mid 90s, these devices were deployed quite a bit before the advent of the regenerative thermal oxidizer really took hold. These devices still get deployed in areas that require a very small footprint, or in areas where you want to fit it into a plant up on a mezzanine or something. And what happens in those cases is that you not only have the primary heat exchanger that's integral to the device, you would then have secondary heat exchangers that would recover the heat off the back of this and deploy it at a process. A good example of that, automotive assembly plant oven. This is up in the mezzanine at the same place as the oven heater boxes are. You use a recuperative oxidizer, you take the heat off the back, and you then recover that for the oven. That's a good example of the application of this device. In its simplest schematic form, it's a burner and a combustion chamber, and we either bring the gases in and we pass them on the outside of the heat exchanger tubes before going through the burner, and then the outlet gases go through the inside of the tubes, or we can design them in reverse. And we'll do that either way depending on whether in the combustion process there's any byproducts of combustion. So in the case where we're seeing a lot of siloxanes and so forth, we may want to have the exhaust gases pass through the tubes so that you can go in and ream the silica dioxide and so forth out on a best practices maintenance basis. Here again, the fields of application are this device. You can see here, depending on the incoming gas temperature and the subsequent outgoing gas temperature, there's a lot of different secondary heat recovery devices that we can deploy. We can integrate them with scrubbers and so forth. With the advent of the regenerative thermal oxidizer, you don't see as many recuperative oxidizers these days because we can achieve thermal efficiencies as high as 95%, and we can make a regenerative thermal oxidizer self-sustain, requiring no supplemental fuel at about 3 to 4% of the LEL of VOC that's coming to us. So as a result, one of the things we do is we look for applications where there are recuperative oxidizers, where we could have an energy saving project and we could replace that device with an RTO because of the dramatic increase in thermal efficiency. These systems can be very large. A typical module can go up to as high as 80,000 SCFM. We can couple multiple modules together. Our largest system is over 1 million SCFM. That's operating in China right now. The common 2-tower style system, which you see on the top of the screen, is basically 2 heat exchanger columns connected by a combustion chamber. We can get up to 98% destruction efficiency of VOC with that device. The 3-tower systems integrate a purge feature that purges unburned hydrocarbons from the tower that's offline. We can get up 99% plus destruction efficiency with those devices. And then, of course, there's a newer rotary valve style RTO, which is a single valve that achieves all the same things as that 3-tower device does, and I'll talk about that as we go on. Typical thermal efficiency is 95%. There's cases we can get as high as 97%. And again, autothermal operation is a very common thing that we try to achieve with this device. More importantly, what we can do with an RTO is we can actually vary the thermal efficiency by bypassing heat out of the combustion chamber. And we can bypass up to about 30% of the gas volume that comes into the combustion chamber through the hot bypass. So if I have a gas stream that varies from a high to a low concentration, I can then design a device that can operate very, very efficiently at low concentrations, and it can also handle the spiking conditions and get rid of heat out of the combustion chamber. So there's a lot of variability, and it really optimizes the device as far as energy efficiency goes. This is what a common oxidizer looks like. You see a 3-tower here. If it was a 2-tower, the cutaway would just be these 2 heat exchanger columns. And so what you end up with is a number of valves, inlet and outlet valves, that direct the airflow. And you have air that comes into the inlet. The air gets preheated through the incoming heat exchanger. The VOCs combust, and there's an exothermic heat that's released. And we then capture that heat in the heat sink or the outgoing heat exchanger. And then we switch the valve direction, and the heat sink then becomes the heat source, and so on and so forth. And we keep flipping the heat back and forth between what is ultimately a ceramic mass heat storage device, and it's a little bit different than what a metal style heat exchanger ultimately is. We get complete combustion in the combustion chamber, so the real inefficiency of these systems is in the valves and in the inlet and outlet plenums. And that's why if we want to get higher destruction efficiency, we want to get 99%. In the past, there's been a 3rd tower, and that 3rd tower is offline, and we purge the unburned hydrocarbons in that plenum back into the combustion chamber for a second pass at combustion, if you will. And that's how we're able to get very high efficiencies there. In the field, you may see 3 towers, you may see 5 towers, you may see 7-tower RTOs that could be sized for as high as 250 to 300,000 SCFM. The fields of application here, again, are multiple. We can handle organic solvents, halogenated compounds, explosive mixtures, depending on how we design the system. There's different types of specialized metallurgy that are involved, depending on what we're seeing in the gas stream. And to go back to what Stan was saying, there's such a wide variety of VOCs. They all have different heating values. They all have different possibilities for reformation as they go through the heat exchanger column. They all have different auto ignition temperatures. So we need to know what the whole profile is of what we're going to see so that we can understand, A, what temperature we need to run the device at, because some VOCs are harder to kick over than others and combust. And so that's all of what goes into our analysis. And from a testing standpoint, it also becomes important to understand what constant we're going to use in the test methodology, as far as is the test methodology based on propane? Is it based on carbon? Is it based on methane? That may force us to rephrase our guarantees a certain way. So those are the different fields of application of the RTO. The rotary valve style RTO integrates all of the same things as the odd tower does, so we get 99% with it. The single valve replaces all the butterfly valves or poppet valves on an RTO. So there's a lot less maintenance, there's a lot less devices. The devices are smaller, they can be skid mounted, they can be pre-piped and pre-wired up to about 80,000 CFM. They're driven by electric valve drives instead of hydraulics or pneumatics, which typically makes them a little more reliable, a little more environmentally friendly. And the one thing that we can do with this RTO that we can't do with other RTOs is that if there are any condensable organics in the gas stream, rather than have to take the unit offline once it gets plugged up with those condensable organics, we don't have to take it offline to bake that material out and restore pressure drop and free the heat exchanger of that material. We can actually bake it out online. So there's no taking the process down, there's no diminishment of full volume flow during that condition. And with all the 24/7 operations out there these days, that can become favorable. So the way that the heat exchanger works is there's actually 12 sections to the heat exchanger, where we have 5 sections on inlet, there are 5 on outlet, there's 1 on purge, and there's another one that's keeping the inlet and outlet gases isolated. And that, incidentally, is the one section that we would use to do that online bakeout I just spoke of. So it operates like an odd tower. Index is 30 degrees about every 15 seconds. The really attractive thing about this particular device is because of the multiple pi sections and the limited movement of the valve, we get very, very little pressure translation back on the process. And so processes that are very, very sensitive to pressure upsets, an oven that could puff, or a coater that could puff blue smoke, this becomes favorable to that situation. The other thing that's very favorable is that the inlet, the outlet, and the purge are all integral to the same housing. And therefore, in terms of the heating of the valve, it sees outlet gases that are obviously hotter than the incoming inlet gases. And so this valve is very favorable for condensable organics because we don't get condensation in the valve. We don't get condensation on the valve surfaces. So we have a continuous metal-to-metal seat that keeps any condensable organics off of it. And then we also prevent that condensation from dropping out with temperature. So that becomes quite favorable in sticky applications and so forth. A lot of times these days we see processes that have things like plasticizers in them and so forth, where we can keeping everything hot creates a far more maintenance-friendly situation. The next device that's usually integrated ahead of an oxidizer, or it could also be integrated ahead of a situation where you're going to recover solvents, is an adsorber. And that's normally a carbon or a zeolite material. It's usually fixed in either a disc or in a rotor. And what we're simply doing is we're converting a low concentration, high volume gas stream into the opposite. So we're turning that high volume, low concentration scenario into a low volume, high concentration scenario so that we have a very small oxidizer and it can operate very efficiently. We actually create a situation where we can make the oxidizer self-sustain, and then we take the heat off of the oxidizer and we actually use that to regenerate the carbon or the zeolite that's in the rotor or the disc. And so what you see down here at the bottom is you see that the vast majority of this zeolite rotor is in the incoming gas stream and it's absorbing solvents. And then when it rotates into an isolated gas stream, we drive heat across the wheel and we strip the highly concentrated solvents off. And what ends up happening in terms of concentration ratio, the normal setup is like a 10-to-1 scenario. So 50,000 CFM incoming stream turns into a 5,000 CFM oxidizer. So in doing so, we not only make it very energy efficient, we also minimize NOx, CO, greenhouse gas development, and so forth. There's some chemistry that gets involved with this as to whether it's zeolite or whether it's carbon. Some things get preferentially absorbed on different components. The limitations of the carbon are typically about as high as we can get, is 97% removal efficiency. And therefore, in terms of permitting, most of the time if there's a carbon or a zeolite adsorption system, the overall system efficiency is going to be 95 or 96%, the way that it's permitted, because we're going to have to couple a 99% oxidizer with a 95 to 97% removal efficiency of the media, and you have to multiply those two together to get the overall system efficiency. So usually these can only be deployed in an environment where a lower regulatory requirement, 95 to 97% overall destruction efficiency, is required. The other important thing about this is they're only deployed on gas streams that are basically coming to us at ambient temperatures. Obviously, we have to drive that zone up and make that zone hotter to drive the VOCs out of the material. So we're limited in terms of temperature and in some cases humidity in terms of what comes to us. This is just an example, flow schematic of what that entire arrangement would look like. This particular schematic shows a recuperative oxidizer that has a primary and a secondary heat exchanger on it. So the primary heat exchanger on this recuperative oxidizer is preheating the incoming gas stream, just like I showed you in the earlier slides of a recoup. And then we have a secondary heat exchanger that's creating the heat we use to send across the media and regenerate it. And that media is continuously rotating. So there's a lot of processes out there that are either higher temperature or dirty, to where if we could ever design adsorbent media to handle those conditions, there's a lot more that we could do. Wood products industry being a great example, and we've tried it. Just too much gum and goo. So, so that's what a schematic looks like there. So the fields of application are a little bit different here. A good example is how much these are deployed commonly in paint applications, where you've got a spray booth and they're simply you've got a manual spray painter. You've got a huge booth with a lot of air volume and very little VOC. They're deployed in the composites industry, where you're making different types of hot tubs or fiberglass layout processes, again, where they have gigantic booths, big volume of air, very low concentration. The media is very, very sensitive to dust. So in most concentrator systems that you see, there could be upstream prefiltration ahead of the device. And that's something we have to examine very closely. Even in a process where the process may have its own filtration, we have to be very, very careful about what's coming to us, because the media is expensive, and the last thing we want to do is plug it up with particulate. The next thing we're going to move into is catalysts, and I'm going to hand back off to Stan for a few minutes to take you through that. And then I'm going to come back for the part of this presentation that's the most interesting to me, and that's discussion of greenhouse gases.
In North America, the advantage of a catalyst, and there's a definition here, I won't go through it, but what a catalyst does, it will combust something at a lower temperature. So it takes less temperature for a reaction to occur. And the advantage of a catalyst is you don't have to spend as much fuel to heat something up. Now in North America, with the price of gas these days and the thermal efficiency that Karl was talking about, it gets a little bit difficult. There are kind of special applications where catalyst works, but for the most part, most of the things with a high thermal efficiency and the low use and the low price of gas, the values of catalysis sometimes get overwhelmed by that. But very simply, it's just catalysts are basically made with a substrate, and on that substrate, which is inert, we put this wash coat. And the real trick around catalysis is how you design that wash coat. And inside that wash coat, we disperse the active catalysts. And that wash coat is designed to get the special properties and to get the dispersion of the real active material. And it can be dispersed on either a metal substrate or a ceramic substrate, as you see here. The upper right-hand corner, you can see how the wash coat is usually just a very thin layer. It's not a very high concentration, but just enough to get the surface area to get the reaction that needs to take place. And going back to what we talked about before, every VOC has its own unique profile across the catalyst. So some compounds like a methanol and ethanol will ignite at relatively low temperatures. Other compounds have to go at much higher temperatures. So be it thermal or catalytic, we need to understand what these profiles are. And if you're dealing with a situation like in a gas-fired power plant, you're inside a boiler where you have a very fixed temperature, you have to understand what these profiles are so that you can make sure that you can design whether VOCs can be destroyed in that application or not. So it's very, very critical. Each VOC has its own unique conversion curve. And you can do what Karl has talked about thermally, you can do it catalytically. You can take those thermal oxidizers and put a catalyst in there in its place and operate at lower temperatures. So you can just put a layer of catalyst in that thermal oxidizer and don't run it at 15 or 1700 degrees Fahrenheit. You can run it at 800 degrees Fahrenheit. Again, though, it has to be situations where you know what the VOCs are and what the cost of that versus the catalyst is versus the savings of running at lower fuel. But most things you can do thermally, you can do catalytically. You just have to see what the relative costs are for doing that. And I'm not going to get into all of those because Karl's already talked a lot about that. Where can you use VOC catalysts? Power generation, you use in natural gas engines and turbines. It can be used in biomass boilers. A lot of industrial waste gas applications can be used. Petrochemicals is a very big use for that. Can be used in paint booths as well. We even do it in kitchen fumes. I mean, if you go to a Quiznos or a Turbo Chef or a lot of other Dunkin' Donuts and you want to get your sandwich cooked in 15 seconds, well, that oven in the back, when they open the door, you don't get a lot of smoke and fume coming out of it. That's because there's a catalyst in the back of that thing. And as they circulate all that convection air through the oven, when they're cooking that thing, it's going through a catalyst and destroying it. And so catalysts are used in a lot of applications you probably aren't even aware of. So you go to a sports arena and they're cooking things, there's no place to vent the fumes. That's because you can use these fast cook ovens. Burger Kings have charbroilers. They put catalysts right on the ovens to help. And a lot of people don't, of course, you know that you put catalysts in cars. We also put them in airplanes. And when you're flying up through the stratosphere, the ozone layer is up there, you don't want that coming into the aircraft cabin. So there are catalysts that are used to destroy the ozone before it gets into the aircraft. The most important thing we want to talk about here, we're going to turn it back over to you. This is your slide here, correct? We want to talk a little bit, and we're going to finish up on here, which I think is more important to what's contemporary to the issues today, is other ways you can deal with methane emissions. And I'm going to turn it over to Karl to kind of finish up for today. Before I do that, I just want to thank you all again on behalf of the ICAC for your attention. You can go to our website, icac.com. All of our member companies are there. If you ever have any questions about technology, we're advocates for the technology. We don't lobby any regulations. We just try to be advocates for technology. And if you want to find out how something works or what it can do or can't do, if you want to figure out about measurement, we have a very active and very expansive measurement division on how to measure emissions. Go there, find the companies, talk to them. They can answer an awful lot of questions for you. I'll turn over to Karl.
I think just one more comment on Stan's behalf is that in terms of SCR, so often we think of the power industry and so forth, and they're large SCRs with a lot of catalysts in them and so forth. But there are a number of SCRs that are applicable to processes as well. Nitric acid plants, catalyst manufacturing plants, and calcining ovens and so forth. And the differences usually between power and those SCRs is you're dealing with much smaller gas volume, but you're dealing with much higher inlet NOx concentrations in those applications. And so that's just something to be aware of and something that can be done. And in those applications as well, we're using the exotherm off the catalyst, we're recovering heat, we're using it as a preheater on the front end of those systems and so forth. So those are kind of unique apart from power in terms of the actual concentrations we're dealing with. This slide came up simply because there's some new devices that have been developed, not only RTO, but smaller gas turbines that have been developed now that could be used in certain gas processing stages or to control certain methane losses from different gas processing stages, compressor stations, and the like. And in a lot of those applications where it's applicable, a lot of those folks already have small gas turbines and so forth. But what's been done is a gas turbine that actually has a VOC combustion chamber on the front of it. And what we can then do is we can take VOC concentrations or low methane concentrations, we can combine it with air or with fuel to present the ideal condition to the turbine. And we can apply this device to a wide variety of different applications, and we can obviously make power with it. So this becomes interesting in terms of not only methane losses in gas processing, it becomes interesting in petrochemical areas, in areas where they're currently flaring. In terms of the research, the technology review recently, and the discussion about flares. There's a lot of inefficient flares out there. There's talk about enclosing flares. And here's a situation where if someone was permitted for an intermittent flare and they're flaring 24 hours a day, they could potentially deploy a device like this, and we could actually take that flared gas material, and we could make power out of it, both heat and electrical. So there's a broad range of possibilities for this type of a device, albeit at this time a relatively small size or low power output. Another good example of this small turbine would be a landfill gas application where we could handle fluctuating gas quality because of the combination of the combustion chamber and the fuel feed on it. And so as the gas volume varies, that's a really good way that we could deal with that variability. In terms of all the different areas where they're venting landfills and they're burning or venting biogas, it's substantial. This is just a good example when we look at it, from the sky at night. You look at the Bakken play, that's all flares right there, and it's growing as big as Chicago, Denver, Minneapolis. So, the issue for that type of a technology here is what are you going to do with the power? But nonetheless, the opportunity is there. The opportunity could also be to deploy an RTO on all of these losses, and again, we could not only control the methane, but we could generate carbon credits with that. Here's an example of a carbon credit situation that is a proven technology that's deployed to a situation where there's a huge amount of methane released, and that's in ventilation air. There's a huge obvious global warming potential. The value of getting methane seems to be a lot more than CO2. The average U.S. coal mine operates at about 0.6 to 1.1% methane, with concentrations of airflow from each mine of about 160,000 SCFM. And that's about 4,000 pounds of methane an hour, 17,500 tons a year, a huge CO2 equivalent value. And in terms of the Climate Action Plan and the strategy to reduce emissions, you introduce the California Carbon Credit Program, you introduce the regional greenhouse gas initiatives and what they're doing, and here's an opportunity to take the device that's well proven, that in some cases industry referred to as a gas hog, and turn it into a moneymaker and turn it into an opportunity to reach the president's initiatives. Various technologies were reviewed to try and control ventilation air methane. We did look at catalysts. We talked with Stan about some of that stuff. We're looking at the opportunity for flares. They obviously use flares at the mines in some cases, but in terms of methane and RTOs, we can oxidize methane at about 0.3% methane concentration. We can self-sustain the RTO. So we get it hot, we send it 0.3%, and it Cadillacs basically. As I just mentioned, most U.S. mines, it comes out of the mine at 0.6 to 1.1. So what we're doing is we're not only controlling the methane, but we're taking the exotherm from it, and we can make a significant amount of energy out of it if we're in a location that's suitable to deploy it to the grid, or if it's a situation where we can't make energy, we can simply destroy it for carbon credit purposes. It's a proven technology. It's deployed in Australia. It's deployed in China pretty extensively. And the first one in the United States is at the Verdeo mine in West Virginia. So the ventilation air methane systems are a very simple two-tower RTO, basically. The difference is that we have to be very careful about the concentration of methane we send it, because the air that we bypass and release from the combustion chamber, you see it's about 1,750 degrees here, but if the methane concentration is too high and that walks up to 1,950 degrees, you've got issues with the metallurgy of the dampers that we're dealing with and so forth. So there's some technique to it, obviously. But this operates just like the 2-tower that I described to you earlier. And like I said, it self-sustains at 0.3% methane. Here's a little bit of an example what we do with the excess heat. So if we send it 0.4% or better, we've got extra heat to get rid of. We maintain the combustion chamber temperature at the typical figure that most people are used to seeing in RTOs, 1,550 degrees. And once we send it that 0.4% value, it'll start walking up in temperature on its own. So we evacuate the extra heat through that hot bypass damper I talked about, and we can transport it directly out of the stack, or we can use hot air or water in combination with the secondary heat recovery coil, or we can run a steam turbine, boiler, or many different technologies we can deploy to use that heat. This is just an example of the system that's at the Verdeo mine in West Virginia. That was 160,000 CFM. We control anywhere from 0.4 to 1.1 inlet concentration. The biggest, one of the big features about this is about 100 feet away is where there's a collection hood where we collect the gas right off the exhaust fan for the mine that ventilates the mine. That hood is a very specialized device because we have to capture the gas coming off of the fan without actually connecting to it. So it's actually a gigantic capture hood, and it captures about 85% of the methane that's exhausted from the fan. And the mine people are very, very sensitive about us not interrupting the dynamics, the pressures of that fan whatsoever. So that particular hooding was pretty specialized. We get about 97% oxidation of methane, and this whole contract was set up on the basis of generating carbon credits. The larger project that we're actually commissioning right now is 700,000 SCFM at the Hanju Steam Turbine Company in China. We are taking the heat off of the oxidizers, and we're generating about 20 megawatts of power. And in that particular case, it was an attractive situation for them because they not only use that power to run a lot of the equipment at the actual mine, but being that it's in China, there's significant community in the area around the mine that they actually will deploy power back to. The concentrations are kind of unique in this particular mine because in China, the concentration of methane in the ventilation air is much lower. And so we did something kind of unique at this particular mine where instead of just the ventilation air methane, we're actually taking enriched coal mine methane right from the coal seam, which is a much higher concentration, and we're blending it with the ventilation air methane so that we tailor the inlet condition of the RTOs to be exactly where we want it. And that, again, is a very, very specialized mixing system that has to achieve very, very high mixing efficiencies and be proven out through CFD modeling because obviously if any of that 6% concentration methane stream somehow sneaks through that air blender, we've got a serious situation on our hands at the RTO. So in this case, we're sending about 187,000 SCFM at 1,750 degrees to the steam turbine, and we're doing about 20 megawatts of power there. This is just an example of the current status of the project. It's pretty unique because these are all of the RTOs that you see here, and all the air that's being deployed back to the actual turbine. And these actual towers that you see in the foreground, we're capturing the methane coming out of those towers. These are big fan towers here. So it's pretty unique situation. In terms of the question that we keep asking in our mind, that's probably the most important message that I brought for everybody to think about, and as a wrap up here, I just noticed all 18 million carbon allowances are recently sold out at the RGGI auction, and since 2008, its electrical generators, its power guys, and their affiliates have consumed 78% of those $1.75 billion worth of allowances. So the EPA's rules have prompted states to evaluate how they can reduce power sector carbon pollution, and we're creating regulations for technologies at the power plant that are very expensive, tough to achieve, some of which don't even exist. And we're kind of scratching our heads going, hey, we have a proven technology, why don't we get it on the feedstock end instead of end of pipe, and let the coal plants keep doing what they do best, making power with coal. So that's the big question in our minds. Using RTOs that are proven. So, and that's I guess the only other comment that I wanted to make in terms of the RTOs is, obviously anytime we're talking about methane, high concentrations, coal mines, and so forth, the issue of safety is a biggie. And we have integrated all of the appropriate safeties in these systems in China and in Australia and here to prove to the coal mine folks that this can be done very safely and very effectively with the appropriate feed-forward controls, the appropriate infrared type analyzers and so forth to continuously monitor concentration. So thank you very much for your time. I appreciate it.